This is the problem that has been asked. So let us apply the result of the central limit theorem statement for two population. As you can see here, I wrote the statement here: x bar minus y bar minus mu1 minus mu2 divided by square root sigma 1 square by m plus sigma 2 square by n. It converges to normal 0 1 when m and n become large. So if we look at this problem here, mu1 is 6.5, mu2 is 6, sigma 1 is 0.9, sigma 2 is 0.8. The sample sizes are m is equal to 36 and n is equal to 49. So if we write down the statement, you have mu1 is equal to 6.5, mu2 is equal to 6, sigma 1 is equal to 0.9, sigma 2 is 0.8, m is equal to 36 and n is equal to 49. So of course you have to calculate sigma 1 square by m plus sigma 2 square by n, that is 0.9 square by 36 plus 0.8 square by 49. So you can simplify this is 0.189. And of course mu1 minus mu2 is 0.5. So what will be the statement of the central limit theorem here? X bar minus y bar minus 0.5, that is mu1 minus mu2 divided by 0.189. This will have normal 0 1 distribution. So now the question that has been asked here is probability of x bar minus y bar greater than 1. So we will use this distribution here. So probability of x bar minus y bar greater than 1, then that is probability of z greater than 1 minus 0.5 divided by 0.189. So that is approximately probability z greater than 2.65. So you can see from the tables of the normal distribution, this probability is 0.004. Try to interpret also this result. We are saying that the average life of the tubes from manufacturer A is 6.5 and for the manufacturer B it is 6. So the difference is actually 0.5. So in the long run, if I say that the difference is more than 1, then the probability of that is very small. That is what is concluded here, 0.004. Now let us consider, so here what I have done till now, it is the distribution of the sample mean. So approximately what we are saying that starting from any distribution, the distribution of the sample mean is normal 0 1. Okay. Now let us also talk about distribution of some other quantities, because we may be interested in the sample variance and some other quantities also. So that gives rise to some other sampling distributions. So other sampling distributions. The first one of them is a distribution which is named as chi-square distribution. So the symbol is chi, okay, which is a Greek letter chi. So chi-square, that is a name here. So let me define it here. A continuous random variable W is said to have a chi-square distribution with n degrees of freedom. So the word here I am using degree of freedom, that is the parameter of the chi-square distribution here. If it has probability density function given by one by 2 to the power n by 2 gamma n by 2 e to the power minus w by 2 w to the power n by 2 minus 1, where w is positive and of course n is positive. So this is one of the sampling distributions. I have to prove that it is a sampling distribution by deriving it as the distribution of function of certain random sample. Okay. So is this form clear to everyone? Is it visible?
Yes, sir.
Can you identify this? Can you identify this? Because we have already done large number of continuous distributions. So is it similar to something which we have already done?
Sir, gamma distribution.
It is a gamma distribution. So I am calling it another name because this is a special case of gamma distribution. Okay. In gamma, if I put r is equal to n by 2 and lambda is equal to 1 by 2, this is actually gamma n by 2, r is n by 2 and lambda is half. Okay. So I am calling it as a sampling distribution and a new name is given. So we will derive it. First of all, let us look at the properties. What is the mean of a gamma distribution? Do you remember? What was the mean of a gamma distribution? Does anybody remember the mean of a gamma distribution? R by lambda. So it is n by 2 divided by 1 by 2. So it will become n. What was the variance of a gamma distribution? It was r by lambda square. So it is n by 2 divided by 1 by 4. So variance of this will become 2n. So it is easy to remember here. The mean of a chi-square distribution is equal to the degrees of freedom. The variance is equal to twice the degrees of freedom. Let us also look at some of the other important things, because for gamma distribution we have already derived all those things. What is the kth moment, for example? That will become n into n plus 2 and so on, n plus 2 into k minus 1. And what will be the moment generating function? 1 minus 2t to the power minus n by 2, where t is less than half. Because this I am writing simply from the moment generating function of a gamma distribution, that was lambda by lambda minus t to the power r. So if you put lambda is equal to half and r is equal to n by 2, then you will get 1 minus 2t, of course in the denominator, to the power n by 2. Gamma distributions, other things also are known to us. So let me just briefly write down those things quickly here. So for example, what will be the third one? Third central moment is 8n, which is positive. Of course, we know that the gamma distribution is positively skewed, and A10 of course is positive. So the form of this is, so it is positively skewed. Chi-square distribution is of course positively skewed, and the fourth central moment, by this general formula you can write down 12n into n plus 4. So if you calculate the measure of kurtosis, that is mu 4 by mu 2 square minus 3, then you substitute it here, so it will cancel out this term here, and you will get basically 12n here, which is of course positive. So it is leptokurtic. But of course you can see here that as n increases, this converges to 0. So it will converge to the kurtosis of a normal curve if n becomes large. Similarly, if you calculate mu 3 by mu 2 to the power 2 by 3, 3 by 2, then that also converges to 0. So as n becomes large, this also converges to normal. Another thing is regarding the points on the curve, like in the tables of the normal distribution are available. Similarly, the tables of chi-square distribution are also available. So if this probability is alpha, then this point is called chi-square n alpha. That means probability of W greater than chi-square n alpha, it is alpha. So in the tables of the statistics, if you see at the end of the book, tables are given for points of chi-square distribution also. So I'll just show, I don't know whether it is visible from here or not. So this you can see here. Okay. So for different values of n and alpha, the tables of the chi-square n alpha are given in the book. Okay. At the end of the book, you see these tables are given. So now let us consider, see these properties I could write straight away because we already know the properties of the gamma distribution. Now let us show that it is a sampling distribution by deriving it as a distribution of certain function of random sample from some distribution. Okay. So one thing that you can observe here, because of the additive property of the gamma distribution, to the power minus n by 2. So the powers will get added up. So you have the additive property of chi-square distribution. So let W1, W2, Wk be independent with Wi following say chi-square on ni degrees of freedom. Okay. Then say u is equal to say sigma of Wi, I is equal to 1 to k. This follows chi-square sigma ni. So the degrees of freedom will be added up. The proof is trivial. You have to just apply the MGF here, because MGF of a sum is equal to the product of the MGFs. So immediately you can prove from there. Is the statement clear?
Yes, sir.
Now let us consider, let us take, say, x follows normal 0, 1, and I define, say, y is equal to x square. Then do you remember the distribution of x square? I have done it in the class earlier. See, you have two inverses here, x is equal to root y and x is equal to minus root y, and dx by dy is equal to 1 by 2 root y, dx by dy here is minus 1 by 2 root y. So the PDF of x is 1 by root 2 pi e to the power minus x square by 2. So this y is equal to x square is 2 to 1 function, and you have two maps, minus infinity to 0 goes to 0 to infinity, and 0 to infinity goes to 0 to infinity. I have written the two inverse images here. So the PDF of y is obtained by writing down the density of x in two different regions. Okay. So 1 by root 2 pi e to the power minus x square by 2, that is y by 2, into 1 by 2 root y plus 1 by root 2 pi e to the power minus y by 2, and mod of the second one is also same value. So if you simplify this, it is 1 by 2 to the power half, root pi is gamma half, e to the power minus y by 2, y to the power 1 by 2 minus 1, which is nothing but a chi-square 1 distribution, which is PDF of chi-square 1 distribution. So what you have proved? That if x follows a standard normal distribution, then x square follows chi-square 1. Okay. So now if I consider, so if x1, x2, xn are independent and identically distributed normal 0, 1 random variables, then W, that is equal to sigma xi square, that will follow chi-square n, because each of x1 square, x2 square, xn square, they will be chi-square 1, and because of the additive property it becomes chi-square n. Is this statement clear? Is it clear?
Yes, sir.
Now
Yes,
I
sir.
will give, so first of all it establishes that chi-square is a sampling distribution, because if I am taking a random sample from a standard normal distribution, then the sum of squares follows a chi-square distribution. So it is a sampling distribution. Now I will derive in another context. Okay. So next, let x1, x2, xn be a random sample from normal mu sigma square. Okay. Suppose x1, x2, xn is a sample from a general normal distribution in place of normal 0, 1. So let us consider what is the distribution of x bar. By the linearity property, we have proved that x bar follows normal mu sigma square by n. So what is the moment generating function of x bar? That will be e to the power mu t plus half sigma square t square. So because sigma square has become sigma square by n, so it will be written like this. Is that okay? Is this statement clear? Because we have already done this part earlier.
Yes, sir.
Let us
Yes,
also
sir.
do some more transformation. Okay. So let us define, say, yi is equal to xi minus mu by sigma. Then by linearity property, this follows normal 0, 1, and y1, y2, yn are IID normal 0, 1. Okay. So if I consider, say, w, that is equal to sigma yi square, that is 1 by sigma square sigma xi minus mu square, then that is following chi square n. Okay. So MWT, that will become 1 minus 2t to the power minus n by 2. Okay. So this statement is also coming from the theory that we have discussed till now. Now let me take another change here. Let me define say UI. So let us just have different names here. I have used x bar here, and then I have used yi's here, that is xi minus mu by sigma. Now I am defining ui is equal to xi minus x bar. Okay. So for I is equal to 1 to n. So let us write down the random vector u1, u2, un. Okay. So let me write here. We first prove that x bar and u are independently distributed. Okay. We will try to show that x bar and u1, u2, un, they are independent. For independence, we can either consider the joint PDF, we show it as the product of the marginal PDFs, or we can also use the moment generating function. In fact, in this case, moment generating function will be easier to handle, as I will show you now. That moment generating function of x bar and u at the point, say, s and t, that is the product of the moment generating function of x bar at s and the moment generating function of u at t for all s and t. T of course is a n-dimensional term. Let us take, say, t bar as 1 by n sigma ti. So we have to calculate the left hand side and the right hand side. Okay. The right hand side, at least one term I know, because moment generating function of x bar I have written earlier. Moment generating function of x bar, here I have written at t, we can write it at s also. So we have moment generating function of x bar at s, that is e to the power mu s plus half. Okay, so we wrote it as sigma square s square. Okay. Now let us consider MGF of u. Okay, so MGF of u, that is u1, u2, un, that is expectation of e to the power sigma ti ui, I is equal to 1 to n. Is that okay? Is this definition clear?
Yes, sir.
Yes, sir.
So we express it, expectation of e to the power sigma ti. What is ui? The definition of ui is xi minus x bar. So this is equal to expectation of e to the power sigma ti xi minus x bar into sigma ti. See, we are defining t bar is equal to 1 by n sigma ti. So we can do some sort of manipulation here. We can write this as expectation e to the power sigma ti xi minus n t bar x bar. That is equal to expectation of e to the power sigma ti xi minus t bar sigma xi. So n x bar I can write as sigma xi. So this can be then written as expectation of e to the power sigma ti minus t bar xi. I is equal to 1 to n. Since x1, x2, xn are independent, we can utilize that here. This is expectation of the product I is equal to 1 to n e to the power ti minus t bar xi. So these are all functions of x1, x2, xn, and since x1, x2, xn are independent, expectation of the product becomes product of the expectations. So this becomes product of the expectation e to the power ti minus t bar xi. So is this manipulation clear?
Yes, sir.
Now, if you look at the last term, expectation of e to the power ti minus t bar xi, this is nothing but the moment generating function of xi at the point ti minus t bar. So this is product of moment generating functions of xi at the points ti minus t bar. Xi follows normal mu sigma square, so this MGF is known to us. So we just substitute it here. So product I is equal to 1 to n e to the power mu Ti minus T bar plus half sigma square Ti minus T bar square. So you take this product into the exponent, it will become summation. Sigma Ti minus T bar is 0. So the first term will vanish and you are left with only the second term, that is 1 by 2 sigma square sigma Ti minus T bar square. Is this calculation okay?
Yes, sir.
Yes,
So
sir.
actually, if you see this term here, mx bar ust is equal to mx bar s and mut, then on the right hand side I have determined both the terms. Now I should determine the left hand side. Okay. So next we consider mx bar ust, that is expectation of e to the power s x bar plus sigma Ti ui. Well, expectation of e to the power sigma Ti ui we already simplified. If you remember here, we have done this calculation here. E to the power sigma Ti ui, I could finally write as expect e to the power sigma Ti minus T bar xi. So we will just use that here. So this will give me expectation of e to the power s x bar, that I write as sigma xi plus sigma Ti minus T bar xi. So I have used the simplification which I did it in the earlier steps. So I am not rewriting that here. Okay. Is that okay?
Okay, sir.
Now again you see this term I can combine here. This s term I can combine with the term given here. Sorry, this is sigma xi by n, because x bar is sigma xi by n. So s by n sigma xi. So this first term here in the exponent and the second term in the exponent, I can take common xi. So I will get it as expectation of e to the power sigma xi Ti minus T bar plus s by n. Okay. And again you see it is having the same structure, that is expectation of e to the power sigma xi. So this I can write as expectation of the product I is equal to 1 to n e to the power Ti minus T bar plus s by n xi, and expectation of the product will become product of the expectations because xi's are independently distributed. So this is product I is equal to 1 to n expectation of e to the power Ti minus T bar plus s by n xi, and this is nothing but the mgf of xi at the point Ti minus T bar plus s by n. So it is product I is equal to 1 to n moment generating functions of xi at the points Ti minus T bar plus s by n. Since xi follows normal mu sigma square, so this term we can write it as product I is equal to 1 to n e to the power let me write it in the next step here. e to the power product I is equal to 1 to n e to the power mu ti minus t bar plus s by n plus half sigma square ti minus t bar plus s by n whole square. So this product will go in the as a summation in the exponent. So you will get e to the power sigma ti minus t bar, that will cancel out, and then s, so it will become e to the power mu s and let us look at in the second one, half sigma square ti minus t bar square, so it will become half sigma square sigma ti minus t bar square. Then the cross product will have s by n into ti minus t bar, so sigma if you put, that will again vanish, and the last one will give me s square by n square. So if you sum s square by n will get, so you will get 1 by 2 s square by sigma square s square by n. So if you compare this 1, 2 and 3, then you get it as direct product of mx bar s and mu t. So this proves that the distribution of x bar and u are independent. So x bar and u is that okay? Now let us look at certain manipulations here. So I have written some quantity here earlier. If you see, I considered a random sample from normal mu sigma square, and then I defined w, that is sigma yi square, that is 1 by sigma square sigma xi minus mu whole square. Okay, let us consider, say, a decomposition of this. Okay, so now consider w, that is 1 by sigma square sigma xi minus mu square. This we write as 1 by sigma square sigma xi minus x bar plus x bar minus mu square. So this is nothing but 1 by sigma square sigma xi minus x bar square I is equal to 1 to n plus n x bar minus mu square by sigma square, and the cross product term will cancel out because you will get 2 times x bar minus mu sigma xi minus x bar. So sigma of xi minus x bar is 0, so therefore the cross product term cancels out. Okay, so this n by sigma square x bar minus mu, that term is coming from where? If you go back again to my first step here, I have written here x bar follows normal mu sigma square by n. Okay, so from here if I standardized, I will get x bar minus mu divided by square root sigma square by n. That will have normal 0, 1. Okay, so let us write it here. So let us call it, say, I'll give some name here. Let us call it, say, W1 plus W2. Okay. Let us look at this W1 and W2. First, we observe that, see, if you look at W2, W2 is a function of x bar and W1 is a function of U1, U2, UN. Okay. Therefore, since we have proved that x bar and U1, U2, UN are independent, it means W1 and W2 are independent. W1 and W2 are independently Is that point clear to everyone? That W1 and W2 are independently distributed?
Yes,
So, you will have MWT is equal to MW1T into MW2T. That is one thing that we are able to observe. Okay. Now let us look at the independent terms, this MW1T and MW2T. This MWT we already have because W is following chi-square n distribution, isn't it? So let us look at what is MW1 and MW2. So W2, this is n x bar minus mu by sigma square. See, we are having x bar following normal mu sigma square by n. So this implies that square root n x bar minus mu by sigma, that follows normal 0, 1. So this implies that this is square here. So W2, because that is square of this, that will follow chi-square 1 distribution. W is following chi-square n. Okay. So MW1T, that is equal to MWT divided by MW2T. And these values we have because it is 1 minus 2t to the power minus n by 2, and this one is 1 minus 2t to the power minus 1 by 2. That is 1 minus 2t to the power minus n minus 1 by 2 for t less than half. This is the moment generating function of chi-square n minus 1 distribution. So we have proved that sigma xi, that is W1, that is sigma xi minus x bar square by sigma square, that follows chi-square distribution on n minus 1 degrees of freedom. So if we define what we call the sample variance, define s square as 1 by n minus 1 sigma xi minus x bar whole square as the sample variance hello. So we define this s square as a sample variance of x1, x2, xn. Then what we have shown that n minus 1 s square by sigma square follows chi square n minus 1. So this establishes chi square firmly as a sampling distribution when we are sampling from a normal distribution. So this is one important point to be noted here, that in sampling from a sample from a normal distribution, from a general normal distribution, the distribution of the sample mean is again normal, but the distribution of the sample variance, of course after certain multiplication factor, is chi square distribution. So this is an important sampling distribution here. Now we define some other distributions also, which are sampling distributions. So is this discussion clear till now?
Yes, sir.
So the next one is students t distribution. Okay. So let me define it here firstly. Let x and y be independent distributed random variables. Let x follow normal 0, 1 and y follow chi square n. Then t, that is defined as x divided by square root y by n. Okay, so let us look at the definition. I am having two independent random variables. One is a standard normal and second is a chi-square. Then if I take the ratio of x divided by square root y by n, then this is said to have a student's t distribution on n degrees of freedom. We write actually t follows t on n degrees of freedom. This is the notation that is used here. So is the definition clear? It is a ratio of a standard normal divided by square root of a chi-square divided by its degrees of freedom, and the two variables are independent here. Is that okay?
Yes, sir.
So just a small comment about that, why we are calling it as a student's t distribution, not a professor's t or parent's t. So this is actually a pseudonym of the person who actually developed it. Actually, it was developed by W.S. Gossett in 1907. But he was working in a brewery, therefore he did not want to disclose his name. So he wrote under a pseudonym, that is a student. So that is why it is came to know as student's t distribution. Now the derivation of this should not be difficult, because you know the distribution of x here, you know the distribution of y here, and you can write down the joint distribution because they are independent. From there you define a transformation, that is t is equal to x by root y by n, and you have already understood that how the distribution of the transformation is calculated. I have solved few examples in the class. Okay, so this is not difficult. You write the joint PDF of x and y, so that is fxy, that is product of the individual distributions because of the independence. So here you can actually see the usage of independence that allows you to write down a lot of things, because if we don't have the independence, then there is no way of writing down the joint distribution. So x is following normal 0, 1, so I am able to write that. The distribution of y is chi-square n, that is 1 by 2 to the power n by 2, gamma n by 2 e to the power minus y by 2 y to the power n by 2 minus 1, where x is a real and y is a positive real. Now we have the transformation, that is t is equal to x divided by, so we take this root n in the numerator, this divided by root y. In order to get a one-to-one transformation, I will need another function. So let me write u is equal to y. So we can find out the joint distribution. So what is the inverse transformation? So x is equal to root u by n into t, and y is equal to u. So we consider the Jacobian here. That is, we have to write del x by del t, del x by del u, del y by del t, del y by del u. So del x by del t, that is square root u by n, del x by del u, that will give me t divided by 2 root nu. Del y by del t is 0, del y by del u is 1. So that is square root u by n. So from here the joint distribution of t and u can be written as one by 2 to the power n plus 1 by 2 square root pi n gamma n by 2. These are the coefficients coming in there. E to the power minus u by 2 1 plus t square by n, and then u to the power n plus 1 by 2 minus 1, where t is of course a real number and u is a positive real. So I have just written the terms as we got them here. That is the density of x and y is there. So we transform x and y to t and u there, and we multiply by the Jacobian in the joint density function. So is this term okay? Is this term okay? In order to get the distribution of t, I should integrate with respect to u. If you integrate with respect to u, you can observe that here this is nothing but a gamma function for u, because e to the power minus u into something and then u to the power something du from 0 to infinity. So it's nothing but a gamma function. So integral is straightforward. So the marginal PDF of t is gamma n plus 1 by 2 divided by all these terms. So there will be 2 to the power that, then that 2 to the power n plus 1 by 2 will get cancelled out with this, and then root pi I can write as gamma half, root n will be there, then gamma n by 2 gamma half, and then this term will become 1 plus t square by n to the power n plus 1 by 2 in the denominator. So if I write in the numerator, I will put minus power minus n plus 1 by 2, where t is from minus infinity to infinity. So this is the probability density function of a t distribution on n degrees of freedom. Is the derivation clear? I have just used the basic principles here of the transformation and written down the joint density of x and y, and from there I just derived the t and u, and since u is redundant I don't need u, so I integrated that, so I get the distribution of t. Is this calculation okay?
Yes, sir.
Now if you observe it carefully, see this distribution looks little bit like normal distribution only. In the normal distribution you have e to the power minus t square by 2 in the standard normal, and here you have 1 plus t square by n to the power minus n by 2. So if you take n tending to infinity, this will actually go to e to the power minus t square by 2. So in principle actually it is quite similar to the normal distribution, but of course when you have the exact sampling distribution, then it is slightly different, that's all, but it is symmetric about 0. So you can see the density is symmetric about 0. Okay, so therefore the odd ordered moments will vanish. Odd ordered will vanish. Of course, those which exist. Unlike the normal distribution, where all the moments exist because e to the power minus t square by 2 is there, but here only it's a polynomial power, therefore all moments will not exist. In fact, we can say that even ordered moments exist of order less than n. Okay. You can write down some specific moments actually. So let me just write that here. Expectation t of course is 0, and variance of t, that is expectation t square, that you can get, it is n by n minus 2. So if n is greater than 2, then this is valid. And mu 4 is, that is expectation of t to the power 4, that is 3n square divided by n minus 2 into n minus 4. This is valid for n greater than 4. So if you calculate here beta 2, that is the measure of kurtosis, that is mu 4 by mu 2 square minus 3, that is 6 by n minus 4. So it is leptokurtic. But one thing is that as n becomes large, it will converge to the kurtosis of the normal distribution. So the peak is, you can say, a little higher than that of a normal distribution. Okay. The concentration is more in the center. And if we consider this point where this probability is alpha, then this point is called Tn alpha. That is probability of t greater than Tn alpha is alpha. So this tables of Tn alpha, they are tabulated. I mentioned to you the tables of chi-square. Similarly, you can see the tables of t. So in all the books of statistics, the tables of t distribution are also given. So I'll just show you here. Of course, it may not be very clearly visible here, but you can just see this. So in any book of statistics, if you see at the end, the tables of the Tn alpha are given for different values of n and alpha. Okay. Now again, let us connect it to the sampling distribution here. So first thing that you observe here is that as n tends to infinity, the PDF of t converges to phi t. Okay, that is the PDF of standard normal random variable. Now let us also look at a random sample from a general normal distribution. Let x1, x2, xn follow normal mu sigma square. So we have a random sample from a general normal distribution. Then this x bar minus mu by sigma by root n, or you can say root n x bar minus this one. This follows normal 0, 1. and W, that is root n n minus 1 s square by sigma square, that follows chi square n minus 1, and these two are independent. Can you see the screen? Can you
Yes,
see
sir.
the screen? Okay. So by the definition of the T, root n x bar minus mu by sigma divided by square root n minus 1 s square by sigma square into n minus 1, that is nothing but root n x bar minus mu by s, that follows T distribution on n minus 1 degrees of freedom. So this establishes the T distribution also as a sampling distribution. Is it clear? So note here that root n x bar minus mu by sigma, that follows normal 0, 1. And if we replace sigma by the sample variance here, sample standard deviation, then it is T distribution on n minus 1 degrees of freedom. So this was actually the contribution of W.S. Gossett, who wrote under the pseudonym student. So he proved that if we are replacing the population variance by the sample variance, then the distribution is not normal, and that is what he derived. Is that okay? So let me move to the next sampling distribution. It is known as F distribution. So let W1 and W2 be independent random variables, and W1 follows a chi square m, and W2 follow chi square n. U, that is chi, so that U I am defining as W1 divided by m divided by W2 divided by n. So I am considering the ratio of two chi square distributions divided by their degrees of freedom. This is said to have an F distribution on mn degrees of freedom. Okay, here 2 degrees of freedom are coming, one from chi square in the numerator and one from chi square in the denominator. Okay, we write U follows F F mn. So we write like this. Once again, the distribution of U can be determined easily, because you can write down the distributions of W1 and W2. They are independent chi square, so the joint density can be written. Again, make the transformation. U is equal to this W1 by m divided by W2 by n, and V is equal to, say, W2. And then you find the joint distribution and integrate out V. So you will get the marginal distribution of U. So I leave it as an exercise to you. Okay, so I leave it to you to do it. This is m by n to the power m by 2, 1 by beta m by 2 n by 2 u to the power m by 2 minus 1 divided by 1 plus m by n u to the power m plus n by 2 minus 1. No, there is no minus 1 here. This. Okay. And u is positive. This is a positive valued random variable. In fact, if you plot it, it will be the plots will be like this, positively skewed. Of course, depending upon different values of m and n, you will get different shapes here. Okay. Expectation of u is n by n minus 2 and variance of u is equal to, of course this is immaterial here because this is actually a sampling distribution. It is not used for moment and all these purposes. The tables of f distribution for different values of m and n are also given. So if we consider so if this probability is alpha, then this point is called f mn alpha. Okay, that is probability of u greater than f mn alpha is equal to alpha. Tables of f mn alpha are given at the end of the books. All the statistics books you see, at the end some table will be given of the f values. So I will show you here. You can see this. So these are the tables of the f distribution. Okay, for different values of m and n and alpha, these tables are given here. So you can see this here. So anyway, check in your own books that you are having. And nowadays, of course, on the internet also you can just search. You can search tables of standard normal distribution, tables of t distribution, tables of f distribution. So these are freely available nowadays because they are also part of standard softwares. Something simple you can observe that if u follows f distribution on mn degrees of freedom, then 1 by u will follow f on nm degrees of freedom. So if we utilize this property, we will get f of 1 minus alpha nm is equal to 1 by f alpha mn. Let us also look at it as a sampling distribution. So let me consider two random samples. In place of one random sample, let us consider two random samples here. So let x1, x2, xm be a random sample from normal mu1 sigma 1 square and let y1, y2, yn be a random sample from normal mu2 sigma 2 square. Let us define, say, S1 square as the sample variance of the first sample and S2 square as the sample variance of the second sample. Then if I take, say, let me give some name here. W1 is equal to m minus 1 S1 square by sigma 1 square. This will follow chi square on m minus 1 degrees of freedom. And similarly, W2, that is equal to n minus 1 S2 square by sigma 2 square, that will follow chi square on n minus 1 degrees of freedom. And W1 and W2 are independent because they are taken from different populations. So you can construct an f variable from here by dividing by the degrees of freedom respectively here. So then you will have that is W1 divided by m minus 1 divided by W2 divided by n minus 1. What is that equal to? It will become simply sigma 2 square by sigma 1 square S1 square by S2 square. That will follow f distribution on m minus 1 n minus 1 degrees of freedom. So the ratio of two sample variances from two different populations, that follows a f distribution. So therefore f is also a sampling distribution. So is this example clear?
Yes, sir.
So I will stop today's class at this point. Tomorrow you have a test, and I already declared the syllabus also. It's on the function of one random variable, the joint distributions, bivariate normal, conditional, marginal, the conditional probability, the joint probability, the conditional expectation, the conditional variance, and the conditional and marginal distributions in the bivariate normal distribution, and also the function of two variables, etc. So the transformations. So the format of the exam is the same, that is, you have to answer 10 questions which are randomly chosen from a set of questions, and you will get around 45 minutes to answer those questions, and it is like continuous. You solve one problem, move to the next one, and so on. Navigation we are not allowing. And then in the next week I will cover the inference part, that is the basic concepts of the estimation and the testing of hypothesis, in the remaining 3 lectures. Okay, I have already sent to you all the various assignments, and for many of the problems I have given the solutions also. For remaining problem you should solve yourself. Okay, so I'll close today's class at this point. Is that okay?
Yes, sir. Thank you.
Yes, sir.
And you should actually, I mean, I have observed the performance is mixed actually till now in the first 3 tests. So so try to do well. I mean, in the last class also, I mean, everybody is not performing very well. So try to see your performance. Okay, that's fine. Okay, so I close the class at this point.